We're going to continue our discussion of the canonical formulation of general relativity with a view to understanding mass and angular momentum and things like that better. Okay, so I'm going to very briefly review some of the things we discussed in yesterday's class. Okay, the action of general relativity, and let me put some numbers now. Now this is a second pass. I'll try to do it a little more carefully. So the action of general relativity is defined as 1 by 16 pi integral square root g times r. And then we had the boundary term, which you might remember was plus 1 by 8 pi times the integral square root. It's h. I'll just check that that's what he calls it as well. Yes, he calls it h. Square root h times k. This was the starting point of our discussion. The next thing we did was to take this r and rewrite it in terms. Okay, so the next thing we did was to set up a coordinate system in space. You remember we had an arbitrary t coordinate system, and we had these lines crossing around. Okay, we had a 3-parameter set of lines crossing an arbitrary level surfaces of an arbitrary function, and the metric took the form ds squared was equal to minus n dt squared plus HAB dya plus na dyb plus nb. What? Say again? dt. dt. Thank you. Okay, let's take 2 minutes to understand this coordinate system just a little better. Okay. There are there are 3 interesting vectors in this case. The first interesting vector, well, it's really an interesting one form, is dt. Okay, is the one form dt normalized so that its norm is 1. This is the normal one form. This we'll call n. N is equal to dt times some number, and the number is going to be chosen so that the norm of n is 1. Okay? This is the normal one form. This is the normal one form of our manifold. Okay? We'll determine this number in just a second. Another interesting vector is the vector that points along these lines. This we sometimes call t. If we've got indices, it's t alpha. It's a vector field that goes along these lines. More precisely what it is t alpha is equal to dx alpha by dt at constant y. Okay, it's in our coordinate system, all the x alphas are yas and vts. So this vector field is 1, 0, 0, 0 in our coordinate system. In a more general coordinate, suppose we had another coordinate system, say some x alphas, such that x alphas were functions of our y's and t's. This vector field would of course be a geometrically defined vector field in any coordinate system. And this would be the definition of this state. You understand what it is? It is the little arrow that goes from one little surface here to the next little surface here. Okay? And along the line like this. Okay? And the length of the arrow is basically how big the arrow is when t changes by 1. Or more precisely, when t changes by delta t divided by delta t. Right? So it's a derivative. It's a tangent vector. So you think of t as a coordinate along each of these curves. And with respect to that coordinate, t alpha is the tangent vector, is the flow vector along that curve. Is this clear? And then there is, of course, a third interesting vector field. The third interesting vector field is this NA. Okay? NA by definition points only along the directions of constant t, because it has only A indices. Okay? So if we look at this thing geometrically, there is this vector here, this TA here, sorry, NA here, and then there is also the normal vector 1 form. Normal to the surface. So what it is the 1 form dt. So that means as an object with lower indices, it's got 1 in the t block, 0 in every other block, times an overall normalization. That overall normalization is going to be chosen so as to ensure that its norm is 1. Okay. Now to determine this overall normalization, what we need to be able to do is to invert this metric. Because the overall normalization of this guy is clearly, so n is equal to dt, clearly divided by square root of gtt with a minus sign. Okay? Now, gtt with a, with lower is this n square plus na nb contracted through this h. Okay? But gtt with an upper thing, the small exercise is too small to be part of the problem here. Gtt upper is just 1 by n square. Okay? So this n is equal to dt divided by n. Say again? N will be in the numerator. You're correct. Thank you. Okay. So now I'm going to ask. I've got 3 interesting vector fields. Okay. It's sort of clear that if NA was all 0, then the metric would be diagonal between t and the y's. Then this guy, when raised, would also point just in the d by dt direction. Okay? So up to some normalization, if NAs were 0, this n and this t would be the same. So n and t would be proportional to each other. But NAs are not 0. Okay, suppose NAs were 0. Then, see, what I've defined here is a 1 form field. What I really want is a vector field, or equivalently what I'm going to do is, right, let's say it this way. What I've defined is a 1 form field. What I want is a vector field. In order to get that vector field, I'm going to have to raise this guy. But because NAs are not 0, this raised object will also have components in the y directions, not just in the dt direction. However, had NAs been 0, the raised object will have components only in the t direction. But there's another vector field that has components only in the t direction. Okay? So, were NA 0, n and t would be proportional to each other. Okay? Now I'm going to find the modification of that relationship when NAs are not 0. Okay? This will give you a sort of geometrical, more geometrical insight into these coordinates. First I'll write it down and then we'll try to prove it. We're going to do a little more trying to prove now in this class, now that we've more or less understood what we're doing. Of course, knowing where to look is very useful. Three plus 1. So this guy claims that t is equal to n times n plus NA. Right. This is a geometrical object. It's a vector field. This is a geometrical object. A vector field. This is a geometrical object. This is bad notation. Okay. That's the scalar n. Can you distinguish? I'll call it n. Now when I write n, it's either a vector or one form depending on context. Okay, is this clear? Is this clear? Okay, so let's see if we can check that this is the case. The only difficult thing about checking this is the case is to remember that while in our definition n is a one form, the other two are vectors. So either we have to lower some indices or raise some indices. Since we have the metric rather than the inverse metric in front of our eyes, it's going to be easier to lower the indices.
But previously we have defined the lowering or raising of NA by HAB. So
now there are two things you can do. You can define the lowering of n by HAB. It's a good question. Just a minute, let me think about it. This is supposed to be an abstract relationship for vectors in 4 dimensions. So you see, if you think of it, let's think of it with indices raised for a moment. This would be T alpha, N alpha, N alpha. This is purely in the alpha directions. Okay, so it's a relationship between 3 vector fields in a 4-dimensional space. It's any.
The first component would be
0, NA. Yeah, so it's just exactly, that's what I mean. In an arbitrary coordinate system, it's 0, NA. Okay? Now, were this equation to be true for vectors, it must also be true if you lower all of them in 4 dimensions. So just in order to prove this equation, not more generally, okay, I will lower this n alpha in 4 dimensions so that I can check whether this equation is true. Just so that because I'm lazy, because I don't want to work out the inverse metric. Okay, if I had worked out the inverse metric, then I would have just raised this n. You understand? It's just an algebraic exercise. That in order to prove that this is the case, I need to show that's equivalent to showing that the same thing is the case for these one form fields, but for that I have to lower n with the full metric. Okay, for this purpose I need to do that. Okay, great. So let me go ahead and do that. Let me go ahead and do that. So this n I already have. N is equal to n dt. What about this t? Well, t is easy because t was just 1, 0, 0 in our coordinate. And so what we get, I'll call this m. Okay, so what we get here is minus t is equal to minus m maybe a sign. I may want a minus here. I had to choose with plus minus.
Yeah.
Yeah, there was some ambiguity. I may want. It's a question of whether I want to point that way. Yeah, I may want to choose. So t is equal to. We'll fix that as we go. So t is equal to minus m square dt.
That is a postulated relation which we are now trying to prove, right?
What?
That relation. That is the relation.
This is. I'm going to check that this is true.
Yeah. That's right.
Yes. So t is equal to minus m square dt plus. Now what do we get? We need HTA. That's simply, okay, I'll write TA If I mix notation, will you understand me? If I write here H
No, I mean T, that will be written as delta
A, B, N, B. Yeah, yeah, you can write it that way. But do you understand? It's the one form. Here I've written in components. This would be your lowered one form for N. Okay, great. And then what about for this guy? Now,
you have written only the AB part here, but T is the zeroth component.
T is the zeroth component, but you see we had, right, what we had here was H was G00 times 1 plus G0, sorry, A0 times 1.
Yeah.
This G00 times 1 was this quantity,
Yes.
and this was the G0 A times 1.
Ah.
This I'll write here with dy. That fixes the notation. Okay, great. And finally, now I'm just wondering, did I get this wrong? It's not working. Just wondering if I quoted the result very happily. I may have to work that out just to check that. Wait, let me let me compute this guy. This is related to your question. Let me compute this guy and lower it. Okay, I'll just compute it honestly and then we'll check the last thing. I may have got this normalization. Let's compute this guy. This guy is what? It was NA upper lowered, so it is GAB D NB dxa plus G0B NB dt. Right, that's what this guy is.
NA. This is
I want the one form that I get by lowering NA.
okay.
I'm claiming it's that. Right? Because what I'm supposed to do is to take n and put any index here.
Yeah.
The indices range from a and 0. Okay, so I get this. So now I just have to substitute what GAB was. GAB was of course HAB. So that's HAB. Okay. G0B was what? G0B was exactly HAB NA. Okay. So now let me check how badly I'm off. I had minus m squared dt plus HAB NA NB is equal to minus m squared dt, okay, plus this guy, this n, and this n we concluded was plus minus. Sorry, let me get my signs right first.
So this HAB NANB should have some dx or
Just a minute. Where was I? I had my, sorry, so where was I? First I want to calculate t. So t was this, and then this was dy. Okay. Now here I had,
and that was also dy.
yeah, this is equal to, I'm really sorry, minus m squared dt, that's good, plus HAB,
That was what I was asking the other day, whether n square is the norm of this in n. Because if that was so, then
yeah, hang on, let me write down the thing and then we'll debug it. Okay, this was t we got right. Yeah, so we got this t right, then this was a minus m squared dt. This I might have got wrong, but anyway, writing it. And then what we wanted was this fellow. There was one term that was sorry, then what we wanted was this guy, which was HAB NB DYB. One term was this, so that cancels this. So that's good. But we had this other term, which was NANB HAB DT. So this dt term is not working. And what would fix it? What would fix it is if I got my normalization of n. Yeah, what is there? Just a minute. No, n is n. Just 1 minute. Sorry. They claim t is n times n alpha plus na. Yeah, like that. Let me just calculate, I'm sorry, let me calculate my normalization of, I'll invert this metric so as to calculate that. I should have done that. I assume this will work. Sorry, let's check that. Let's do this in the case that there was just one y. Just 2 cross 2. Okay, so then our metric is what? It is minus m squared plus h n squared. Okay, then we will have hn and h. This is our metric. Okay, let's see what our determinant is. Determinant is minus m squared h plus h squared n squared minus h squared n squared. Okay, great. So now determinant, so what we do, we take 1 over m squared h, and then what are we supposed to do? We're supposed to flip these. These guys stay where they are, maybe pick up a sign.
no, I think yeah. So because it's symmetric, then it's factor.
Yeah.
This minus m. This is minus m squared h.
Minus m squared h. Good.
Yeah,
Minus m squared h.
The first entry is h.
H minus m squared plus hn squared, and then minus hn minus hn.
So g00 is minus m squared.
Is 1 by m squared, as we said it was, right?
Yeah.
Yeah. What have I done wrong? I'm sorry. Just 1 minute. What have I done wrong? Just give me 1 minute. What have I done wrong here? They certainly claim this relationship is true. Give me 1 minute to get this straight. I lowered this correctly. Looks good to me. Let me just do it one other way. I'm sorry. We'll take 5 minutes to get this straight. Let me do this one other way by writing down a formula for the inverse metric and do it by raise and see if we fare a bit. And then we figure out what the problem is. This thing, firstly, what is this m squared? We'll write this as 1 by m squared into 1 minus n minus n minus m squared by h. What is this? I know what this is, right. Plus n squared. Okay, now I want a natural index structure to attach to this when I go beyond 2 cross 2. There is an obvious index structure to attach to it, which is 1 by m squared times 1 minus na minus na, and then this is minus m squared HAB. Inverse of h, okay, plus n a and b. Clearly this is the only reasonable index structure that will reduce to that when it's 2 cross 2, so it must be right. Okay, so this is the inverse metric. Now I'm going to do the following. Is there a minus? You helped me there. Yeah, minus probably. Shall I check that by checking that when I multiply this with this, I get the 1 in the first column. Yeah, I think that works because the minus m squared into this minus. You see, the minus m squared into minus 1 by m squared here gives 1, and the other two terms cancel each other because that comes with a relative plus and minus. Okay, yeah, thank you. Okay, so now I will take that metric, remove this part, and I'll look at this as a relationship between vectors. So this guy was del t, del by del t. This guy was na del by del ya. What is this guy? This guy is equal to question mark m, and then this is g mu t. Okay, now what was this g mu t? Gtt was minus 1 by m squared. And we needed to normalize this. So this was d by dt with norm what? With norm m. So m squared. Great. So we get minus 1 by m squared. Oh, but we chose norm minus m. Okay, so we get here, so this whole thing is equal to minus 1 by m squared d by dt. That was from here. And then plus 1 by m squared na del by del y. Everything here is multiplied by minus m squared. Okay, plus na del by del y. Now this way it works. So we've done something wrong that way. It has to be just an algebraic mistake because we're doing the same calculation. I won't try to clear that. When we get one way working with an eminent textbook, we'll believe. I'm sorry, I don't know what I messed up on there. I messed up on something in my first attempt. I just got lazy. I tried not to invert this metric. Sorry about that. I hope it was not something conceptual I messed up on. Anyway, let's keep going. So this was supposed to have been 5 minutes. It's taken half an hour. That's my incompetence. But okay, so this relationship is what you want to remember. Okay. Now in this Hamiltonian formalism, what was this T alpha? T alpha is the direction, is the motion that your Hamiltonian should generate translations. Because T alpha is just del by del t. And your Hamiltonian is generating t translations.
So I want to ask a question. So what's the use in separating T alpha into this part?
It's just so that you can help understand what's going on. You've got the slicing. And T alpha is the direction along which your time is moving. When we work out Hamiltonian formalism, the Hamiltonian generates motion in t in this sense at constant y's. That's what it's doing.
Yeah.
Okay? So T alpha is the direction of the motion in which that your Hamiltonian is generating, and you want to understand what it's doing. So what it's doing is generating some motion normal to your slice and some motion in your slice. Okay? So just to understand what Hamiltonian you're building. You've got the slicing, and because of these non-zero NAs, you've got a slicing, you've got a normal to the slicing, but you've got the motion, direction in which you are moving. The Hamiltonian is generating that motion. It's Hamiltonian's generation motion along a vector field. That vector field is partly normal to your slices and partly tangential to your slices. Okay? This M, this lapse, gives you the normalization between normal vector and the direction in which you're moving. And this N alpha tells you how much along the slices also you're moving.
So roughly the N alpha, that would be the evolution as seen by an observer on the slices.
The part of the evolution as seen, yes. Yeah. So roughly what motion in t is doing is moving you from one slice to the other as well as translating you within the slice. Okay? And N alpha is how much you're being pushed along within the slice. Is this clear? Excellent. Okay. Now, the next thing we did was to write down the Hamiltonian. And for that, what we did was we used the Gauss-Kodacki relationship, which was that R was equal to, well, there was a bulk term and a total derivative term. The bulk term had an R3, of course. Okay, and then there was plus KAB minus K squared. Did I get the signs right? okay, R3 plus KB minus K squared, and then plus there was this boundary term. And then there was minus 2 times n dot del n, let's call it alpha, right, minus n alpha of del dot n, and then the whole thing total diverges from that. Right. So this was the relationship for the 4-dimensional Ricci scalar. Then we plugged that guy in here. Okay, we used the fact that square root g was equal to square root h times what we call m. So writing this whole thing now in terms of square root h, what did we get? We got that s was equal to 1 by 16 pi integral square root h times n times r m, r3 plus kb minus k square, okay, and then minus integral square root g minus 2 integral square root g n dot del divergence of del alpha n dot del n alpha minus n alpha del dot n. Okay, all good? Okay, we also had, of course, the action, the part of the action which was here. So this became minus 1 by 8 pi because there was a 2 and it was 1 by 16 pi. And then there was the part of the action that was here, that was 1 plus 1 by 8 pi integral square root h k. Okay?
The first two integrals are over 4 volumes, and the last one is over 3 volumes.
The first two integrals are over 4 volumes, and the last one's over 3 volumes. Correct. So this guy is at the, so imagine that we've got some slicing of space. There are lines of constant t. Okay, this is the boundary of our space. Okay, this integral, if I call this whole thing r, this integral is over r, this integral is over r, but this integral is over b, where b is the boundary. Okay, it's some bound.
Space-time boundary, or I mean,
it's the boundary at what do you think of as spatial infinity? We could also consider finite times. But let's imagine t goes from minus infinity to infinity and forget those guys.
There's no boundary.
There's no boundary there. Actually, you can deal with that, but that's an extra complication that we want. Will play no essential role in it. This boundary will play a big role. Okay, because that's where we'll define our energy. Okay, great. Now let's keep going. Now the next thing we did was to, this was a total derivative. So we integrated it by parts. Okay? So this was a total derivative and we integrated by parts. So what are we getting? You see, the original integral was just over space-time. Okay? But this integral now is making an important reference to the constant time slicing. Okay? Because this n alpha is the n alpha of this constant time slicing. You understand that, right? There are two natural and important normals in the game. There's the normal to this b, and there's the normal to the constant time slicing. And this n is the normal to the constant time slicing. Because what we've done is taken r in the bulk and re-expressed it in terms of slice quantities in the bulk. Okay? So now we're going to get something sort of interesting. So let's see what we get. You see, what we're going to do now is to integrate this by parts. So we get minus 1 by 8 pi, and this becomes integral h, and then we get n dot del, okay, n dot del n alpha dotted with, let's call it r, which is the normal to this boundary. Okay, something we will do is to choose this boundary to be of the form some f of y a is equal to 0. We'll choose the boundary to be independent of time. Okay?
This is the boundary of one slice.
This is the boundary of one slice, but it's also the boundary of every slice, because we're choosing it to be independent of time. So we're choosing a boundary of space-time.
So isn't that a very restricted choice?
Well, it's a convenient choice. You know, this is a fake thing. Right? Space-time is going off to infinity. So we can cut it off the way that's convenient for us. We're going to cut it off in a way that is convenient for our problem, well suited to our slicing with constant t's. Okay? So, you know, if you take d of this normal vector, d of this is the same whether regarded within a slice or in space-time, because it's just d of some, you know, function of y's. So the one form normal to this thing is the same whether within a slice or in all of space-time. Okay? So let's say that quantity was r, and what we get is this thing here. We get this minus n alpha del dot n r alpha. Which, no, these two root h's are the same, because this both root h's on the boundary B, right?
Only for that one.
We've never introduced a root h. Oh,
That root h is on the.
there was another. Did we call that h? Okay, I'm sorry. This is a very bad notation again. There's another. You're right. There's another. A constant time slice that has not made any appearance. Okay, every root h here is the root h on these boundaries.
But not that.
Not this root h. You're right. I'm going to call that h tilde. Okay, that's on constant time slices. Yes, if that was your comment, you were right. This root h tilde is nothing to do with this root h. Boundary time slice. Okay. Now you see that this quantity and this normal are these two things are normal to each other.
Yes.
So this quantity is not there.
And this morning I was learning why they should necessarily be normal to each other, because I mean the constant time slice could curve in such a way that it meets the spatial boundary at some angle, and it does not meet the spatial angle, spatial slice perpendicularly, so to speak.
Yeah. So let's see. So the normal vector n is normal to any yes, let me fix that just a minute.
Oh, because the
only y.
only y.
There is no independence.
That's right. That's right. Yeah. So
There is no component
yeah.
in the DDD.
That.
The only problem with that is that that's for the downstairs thing. Let me get that argument straight. Just a minute. Just a minute. Give me one more minute. Mm-hmm. Put everything right. Ah. Wait, I have to check whether in this Gauss-Kodacci formula yes, just one second. Maybe it's just, let me go through with my manipulation. I'll keep this, I won't set it to 0. Let me go through with my manipulation and maybe, what was this? This was n, it's r alpha. Let me finish this manipulation and see if there's something that cancels. Maybe it's just wrong. Let me just quickly finish this manipulation and see what I get. See what this guy says. Okay, for this, let me just continue with this guy and see what I get. We've got integral square root h n dot del n alpha r alpha So this we'll write as integral square root h n beta del beta n alpha r alpha and then the idea is to integrate this somehow by parts. I want to get part of the extrinsic curvature. Yeah, let me see what he does. Maybe that will cancel something here. Just sorry, just no, just 1 minute. Let me see what he does. Interesting. Let's see. Now let's integrate this by parts. So we get my 2 terms. Are my signs working out right? Up to I get 2 terms. One of which C will be a del dot n times r times n, which is the same as what we have here. Del dot n times r times n. Okay, and the other of which is del on n and then r and n dotted with r and n. So sorry, del on r dotted with n and n. Okay, so if the signs are working out right, that term will cancel this term. Okay, so I didn't need it to be 0. Actually, he claimed it was. I think he claimed it wrong. Okay, that term will cancel this term, and what we'll be left with is a term which is integral h, which is del alpha r beta.
But the signature is not known. The relative signature is negative. Now, if you do a by part, then it will again
bring a minus sign. You are saying the sign is such that it adds up. Okay. Let me leave to next time clearing up why this term is apparently not there. Okay, this term, neither this nor twice of it is there, apparently. I need to understand why. Have I started with the right thing? I'll check this and I'll check this and tell you why. This guy claims we have used n alpha r alpha is equal to 0. Maybe it's true. Anyway, let me think about it and tell you. Okay. What remains here though? What remains here is I'll think about maybe he's demanded that n goes to 0 at the boundary. Maybe part of his boundary conditions is NA is equal to 0 at the boundary. If that were the case, then everything would be good, right? Okay, I would have to look more carefully at maybe there is a requirement he's put that it's generally not necessarily 0 everywhere, but we have to solve this problem with some boundary conditions, and maybe this is part of his boundary conditions. Let's tentatively assume we're doing this.
Maybe the boundary condition is just NARA is 0, right? Or N alpha.
A boundary condition is a boundary condition on induced metric at the boundary. Okay, so it would be something like, let's tentatively assume this is the case. I'm not sure it's the case. I'll get back next time for why this vanishes. Okay, but what you see here is that this is the part of this extrinsic curvature. So let's think of this way. What was this kappa here? This kappa here was equal to k alpha beta times h alpha beta, where h was the full metric on the boundary. Okay? Now, if we decompose, I think he's doing something like this. Because once again, this may only make sense in that.
The tangential and normal.
Normal, that in this direction, at the boundary, this and this are orthogonal somehow to each other. I think there's an assumption going. I'll clarify it next class. Okay? But if we decompose this H alpha beta into, into a projector, which is K alpha beta, H alpha beta minus R alpha R beta, okay, plus R alpha R beta. Okay, then what we're seeing, sorry, n. K was del R.
This should be R, right? Because R is the normal to the.
No. K is by definition orthogonal to R.
Yes.
So K is an object orthogonal to R.
Okay. So you are decomposing it in terms of M.
I'm decomposing it in terms of N. I've got this boundary here, which has a 3-dimensional tangent space.
Yes.
And decomposing in the direction of N and orthogonal to N. Okay, so this would be the K of a constant time slice along the boundary. Exactly. So suppose we take a constant time slice and look at the boundary of that constant time slice. Okay, and ask for the extrinsic curvature of the boundary of that constant time slice regarded as a boundary of the constant time slice. That object would be this, at least assuming something like this. I need to clarify if I'm assuming something about NA vanishing at the boundary, which I suspect I am. Okay? At least assuming something like that. This object would be the curvature, the extrinsic curvature of the constant time slice, of the boundary of the constant time slice, regarded as a submanifold, as a boundary of that constant time slice. Whereas this whole thing here was the boundary of the whole thing in space-time.
Could you please repeat that?
Yeah. Suppose I take this picture. K was the extrinsic curvature of this boundary B in space-time.
Yes.
Now there's a separate geometrical question you could ask. Consider any constant time slice. What is the trace of the extrinsic curvature?
At that instance of.
Yeah, so now this is a 3-dimensional manifold which has a 2-dimensional boundary.
Yes.
Okay? This is a separate geometrical problem. The separate geometrical problem is compute the trace of the extrinsic curvature of this geometry, of this as regarded as the boundary of this.
Yes.
Okay? Now this is a trace of an extrinsic, that this extrinsic curvature is a 2 cross 2 dimensional matrix.
Yes.
This extrinsic curvature was 3 cross 3 dimensional matrix. At least intuitively, modulo 1, I have to check whether, I think, at least if this is the case. Okay? Then this, to get to the 2 cross 2 from the 3 cross 3, what we want to do is to take not the trace of all of K, but the trace of K projected orthogonal to this. But this is the projector orthogonal to this. Clear? At least if this is the case. Let's assume this for them. Then everything is clear because these two are orthogonal directions. Let's assume this for now, and if we can go do better than this, then I'll get back to you about it. Okay? But this part just cancels what we got from here.
This kappa is not equal to this K square. This kappa square.
This kappa? No, this is totally different K.
This is the trace of.
This is K of constant time slices.
And that is.
This is K of the boundary.
The 3-dimensional boundary.
Okay, sorry, there's a lot of, but try to understand this from context. Right? So this had nothing to do with that. Right now we're just looking at the boundary terms. On the boundary we're only looking at extrinsic curvature of the boundary. Okay? So you see that what we get here is basically it turns this kappa into what you would call K. where K is the extrinsic curvature
on a two-dimensional hypersurface.
on a two-dimensional hypersurface of the boundary.
Of the constant.
Of the constant time slice. Okay? So the role in life of these total derivative terms is to take, in this Hamiltonian formalism, this beautiful extrinsic curvature term and convert it into an extrinsic curvature of constant time slices. And this is the thing I wanted to motivate for you. It's certainly true if n goes to 0 at the boundary, which perhaps is the case, perhaps is needed for these manipulations. I'll get back to you about this. Okay, certainly if that's the case.
T dot r is definitely 0.
What?
T dot r is definitely 0, but not n dot r. Yeah, because f is not
What?
dependent on t, so that's why n is equal to 0 is needed. Exactly right. T dot r is always 0 because r had only a components downstairs and t had only one time components upstairs. So these were definitely, when they contracted, they were definitely 0. But that was not true for n, because n had some mixing. But however, if this was 0, then everything I'm saying works. We need to put boundary conditions on the boundary, and it's plausible that certainly in every situation, but I'll check if there's a more general. Let's for now assume we've done this. Then we're happy. Okay? So great. So that's so now what we have is a rewriting of this action into, so I just rub both these terms out and replace them by minus 1 by 8 pi integral square root h times k, okay, where k is the extrinsic curvature of the boundary of the constant time slice, regarded as the boundary of a constant time slice.
Also a three-dimensional integral.
It's also a three-dimensional integral because we've got the whole action.
Yeah. No, I mean, so this is somewhat modified in a way. The earlier extrinsic curvature term, the usual given second term, is modified.
It's modified just because we're taking a part from the bulk, which was a total derivative, taking that to the boundary, and adding it to the other, to the usual extrinsic curvature term.
Yeah.
Okay? Of course, there's a nice, generally covariant way to write it, in which it's this. But once we do this time slicing, this is a natural way to rewrite. Is this okay? Great. What? Small k in general depends on everything. However, yeah, in general depends on everything. Yeah, it depends on everything. For instance, in a space-time in which you've got radiation going out, okay, k will start depending on how much radiation is going out. So it will depend on time at any finite r. Okay, great. Of course, we take r to infinity. Then any fixed, and you allow certain kind of processes, you allow only radiation coming from a finite distance, you won't have time to reach it. But in general, it depends on time. Okay.
This scale is a trace of a two-dimensional space.
Exactly. Exactly. Now the next thing I want to do for you is to go through one or two other things we talked about in the last class, which is converting this action into a Hamiltonian. Okay? So I said most of this, but without any attempt at derivation. In this class, we're going to try to do some rough derivations. Okay? So the first thing that I'm going to continue to assert without derivation, but this I'll give you as an exercise because it's quite easy. Exercise KAB. Now this is KAB of the constant time slice in the bulk. Okay? Is equal to 1 by 2m HAB dot minus del A N B
minus del B in A. You may remember I asserted this last class. Okay. The exercise is to compute it. This is not a hard computation because you know we've just computed n, the normal vector. Okay. So all you have to do is to compute the covariant derivatives of n. Now these covariant derivatives have a part which is covariant derivative in the 3 slice and a part that is out of it. Okay. The part that is out of it essentially depends on HAB time dependence. Okay. So this is something that you can, by definition of the extrinsic curvature and working out a few Christoffel symbols, you can compute. Okay, so this is an exercise for you guys. Okay. Once we've done this, now let us, at least roughly in formulas, look at the bulk part of the action. Okay, look at the bulk part of the action. So the bulk part of the action was integral R3 plus KB minus K squared. And what was this? This had an M and a square root H tilde. Okay. Now I want to understand what are the canonical momenta of my problem. Now this is easy to figure out, so let's figure it out. Okay. So PAB is equal to del of all of this, del that stuff, whatever, del of this by HAB dot, del HAB dot by definition. Okay. But that is same as del of this stuff by del KAB times del KAB by del HAB dot, which is 1 by 2m. So we just have to vary this with respect to KAB. Okay, but we see the case in front of our eyes here, so it's an easy exercise. Okay, so basically what I have to do is take this and see how it varies with respect to KAB. The coefficient of that divided by 2m is the canonical momentum conjugate to H. So let's do the variation. So the variation is square root H tilde times m times, now we'll get a factor of 2 clearly, times delta KAB, okay, and then minus exactly delta KAB H tilde AB times K. Yes, there's a factor of 2 overall outside the whole thing. Okay, but then we're supposed to divide by 2m. So we divide, do this. Then we're supposed to take the coefficient of delta KAB. Okay, so you see that PAB is equal to square root H tilde KAB minus H tilde AB K. Well, this is one of the formulas I presented for you in the last class. Is this clear? Now the next thing we're going to do is to take this formula and to go from the action to the Hamiltonian. This is not so bad. So let's do it. Well, firstly, there's this R3 piece that goes along for the ride. All the action is in the K's. Okay, so what we want to do is to compute the Hamiltonian, which has a term. Let's compute 16 pi times. 16 pi times the Hamiltonian. 16 pi h. A term there is equal to integral minus, you know, what we want is p q dot minus L. Okay, so what we get, a term will be minus h tilde m into R3. Okay, that is just going to be there. We'll add it right at the end. Plus, there is a minus KAB plus K square, again times minus square root h tilde m minus h square K square. Thank you. That's there as well because that's in the minus edge. Okay. Then there's the PAB, but we know what PAB is. So that's square root h tilde into KAB minus h tilde AB K times HAB dot. But
HAB dot has inverted in terms of K.
Exactly. I gave you a formula which I've unfortunately rubbed out, so I'm going to need help from somebody. KAB is 1 by 2, and so 2m KAB plus del B plus del B, yeah, del BNA is equal to HB
dot.
B dot. So everything, thank you.
No. The
One.
first one.
Okay, excellent. So we just multiply this with the plus. Okay, excellent. So now we have terms involving n and terms that don't, not involving n. Let's first look at the terms that don't involve n. Okay, the terms that don't involve n are what? There is k squared minus k squared. But let's look at the sign. Where here it came with a minus, here it comes with a plus. It's the usual thing with kinetic terms, right? Okay? And here it came with a factor of 2. You should think of this as the analog of the half q dot squared.
Yeah.
Its sign gets flipped in the Hamiltonian.
Same.
So basically when you keep the terms that don't involve n, this is just plus. Okay, and then remove this term. Is this clear? I maybe did it too fast, but is it clear? So I had 2m kb, and by removing this term I flipped this sign from minus to plus. This, by the way, makes it very clear that in this way of thinking of the action, you should think of this as potential in this slicing, and this as kinetic. Right? It's very clear because this is the part that depends on time derivatives, where this by definition is a 3-dimensional curvature, so it's independent of time derivatives. So clearly this is a potential term, whereas this is sort of like a kinetic term. And we're seeing it work very nicely. Despite all the shifts, okay, this thing flips sign apart from what's coming now.
So just one more question. So,
Yes.
Finally, the Hamiltonian should be expressed in terms of the canonical momenta. So, and maybe I'm jumping the gun, but we should finally be eliminating KAB in favor of PAB too.
Yes, we should be, but there's such a simple relationship between the two. Namely this, we can take trace of this.
Yeah.
So the elimination is a very simple one. So the relationship between K and P is very close. Okay? So once we've expressed everything in terms of K, just think of K as a function of P. And we can do it, but it just makes it more. Okay. But a good point. Now let's look at the remaining term. The remaining term was this guy. Now this was symmetric, but this was automatically symmetric, so we can take any one term. Okay, so this is 2h tilde 2 square root h tilde, and then this was del a n b times k b minus h tilde a b k. And then what I do is write this as pulling out a total derivative minus 2h tilde nb b del a of k a b minus h tilde a b k. This is the form I want because I can now freely vary with respect to nb. Because there were no derivatives inside.
The total derivative term would
As you know, exactly. As you know, when you're varying an action with respect to a derivative, you can't just set the coefficient of that to 0 because there are boundary conditions. The boundary conditions I'm going with at the moment are n vanishing at the boundary. Okay? You can't. However, once you integrate by parts, then the coefficient of that object by itself you can really set to 0. Therefore, we have seen something new happening here. Okay. The new thing we are saying is that there's a new boundary term.
See, isn't it recursive? I mean, every time you will get some boundary term and we have to fix it by using some boundary term.
But fix it by giving some boundary.
It will create a boundary term.
This will create a boundary term. Correct. This, see, we had a particular boundary term in the action. That was over. Now in going to the Hamiltonian, there is a natural way in which we want to divide it up into bulk plus boundary. Okay, this all came from this business of the Hamiltonian. It all came from the PQ dot. It's not like we're doing something again and again. We're computing different things and therefore getting different boundaries. Yes. Exactly. That will give you something a little different. It's just sum of two terms. Okay? So in this situation now we've got this new boundary term and then this additional bulk piece. So first let's look at the bulk Hamiltonian. The bulk Hamiltonian is this plus this plus this. Okay? Now maybe I should write that down just for clarity. I'm dividing up the Hamiltonian into bulk plus boundary, and just for the bulk, h is equal to 16 pi h. 16 pi h is equal to square root h into m square root h into m into minus R3, it's opposite of this, but the remaining guys are the same sign as this, plus kb minus k square. That's the term with m. Okay? And then the remaining term had no m in it. Why? It's because oh, did it happen in? It shouldn't happen in. H dot came with a, this thing was H dot, right? This came with no m. Right, and that had no m in it either. Excellent, so no m in it. And so the remaining term is minus 2 square root, maybe minus 2 square root h no m, but NA del A of KB minus K squared H tilde AB.
NB, NB,
What?
and NB del A.
NB del A. Thank you. Okay? Now, the bulk part of the Hamiltonian is entirely this object. Now let's do it the way, let's think of it logically the way Upmanyu wants to think of it. What is this a functional of? Okay? What is it a functional of? This bulk part of the Hamiltonian is a functional of P and Q. Okay? Thought of as a functional of the P's. All of these K's are essentially P's. Okay? So these K's are elementary objects in themselves. You should not think of these K's as functionals of these N's, or they by themselves are elementary objects. Logically speaking, you should think of them as P's, or the functions of the P's that you. Is this clear?
Let's say the spatial derivatives of H, they are also the coordinates, right? I mean,
Yes,
the
yes,
Q variable.
those are part of Q's.
Yeah,
Because
I mean, del HAB or something.
Exactly. Exactly. So HAB, the whole function on a slice, and therefore all its spatial derivatives,
Yeah.
are the Q's. Okay? These K's are the P's conjugate to those Q's. And then in addition you have this M and this N, but no momenta conjugate to M and N. Okay? Therefore Hamiltonian's equations will now assert that the momentum conjugate to M and N, which must be 0 because the momentum is 0, must vanish. Okay? So written, thought of this way in this logical structure, the only appearance of M and N is what you see. And therefore the equation of motion is simply the M equation of motion is that this vanish, and the N equation of motion is that this vanish. Okay? And therefore we find the Hamiltonian constraint and the momentum constraint coming out of the Hamiltonian equations of general relativity. Okay. So in the bulk what is going on is totally clear. Is this okay? Okay? Of course you also have the other Hamiltonian equations. That is, that you have the equations which tell you that the
Moment
time evolution, that H
of the coordinate.
H dot is derivative of Hamiltonian with respect to P, and P dot is derivative of Hamiltonian with respect to K. Now H dot is derivative of Hamiltonian with respect to P. What will it reproduce for you? Exactly. So H dot is a derivative of Hamiltonian with respect to P, will give you a relationship that will give you a relationship between PAB and H dot, or equivalently between KAB and H dot, which is this relationship. H dot is equal to this. You will get back this. That's how it always works, right, in this Hamiltonian business. One of the two equations just re-expresses a definition. Right? Okay. For instance, if you were doing particle motion and you took the Lagrangian x dot squared by 2 minus v of x, then Hamiltonian language is p dot squared by 2 plus v of x. Then derivative of that Hamiltonian with respect to p is p, but that's x dot. That's just re-expressing the canonical relationship that x dot was p, that p was x dot. So the equation with respect to p is usually the trivial guy. It's the equation with respect to coordinate, that's the non-trivial guy. Right? So once again we've seen that the equation with respect to p, variation with respect to p, is sort of very simple. What's much harder is to vary with respect to h. That I'm not going to try to do. That's harder because it involves all of this kind of stuff. And H's are all over the place. They're there in contracting indices. H's are the most complicated things. They're there all over the place. Okay? This is the hard equation, but I'm going to tell you what it effectively amounts to. After a lot of work, you find the following equation. KAB dot is equal to M del A del B of M minus M times RAB plus KAB minus 2 KAB, KB, KAC, KCB plus Lie derivative with respect to the vector n, this lattice shift vector, okay, of HAB. You know, this Lie derivative with respect to the shift vector of HAB is simply reflecting the fact that what you are doing is computing d by dt holding, going along some essentially arbitrary direction. Do you understand what I mean? Let's remember what our slicing was. We had the slicing of space-time, and then time evolution meant moving from where? Well, from this slice to this slice, but that's not enough. When I say dot, it's not enough to say this slice to this slice, I have to tell you where. And we chose these arbitrary curves to define where. The direction of those curves were these ends. If I change these ends, I change what I mean by evolution without necessarily changing anything physical. I can take the same space-time and slice them with different curves. Okay? So clearly there will be a part of this evolution that will be trivially related to motion in the n direction. That's this. The rest is the non-trivial part. In this you could have predicted. Okay? This is somehow more or less the trivial part. This part is less trivial. Okay? This is the analog of the equation P dot is equal to minus V prime in particle mechanics. Okay, this is P dot, and this is your minus V prime. Now this V prime is a very complicated V prime, but it's okay, whatever you have. Okay, what have we bought from the point of view of the bulk by doing all of this? We bought 2 or 3 things. Firstly, we have explained to ourselves how we can on a computer solve Einstein's equations. This is not an entirely trivial thing, because when you write down, when you think of differential equations, in your mind you want to be able to think of it as something you can put on a computer. In your mind you want to think of it as, well, I'll give you this data, and then the differential equation tells me how to go one slice to the next slice to the next slice. That's how Newton's laws are. That's how Maxwell's equations are. However, it's not so clear that that's how Einstein's equations are, because what is the slicing for which you do this? It's so beautifully invariant, so beautifully generally covariant, that it obscures the structure. One question you want to ask is, can you put back the structure? Okay, not in a completely canonical way, by which I mean in a way that involves choices. Can you recover the structure of, I specify some data on a slice, and your computer will tell me what happens in the future. Okay? And this is now what we're doing. The data we're specifying are k and h. Okay? Plus, of course, this shift and lapse. That is something, it's sort of arbitrary. Do you understand that it's arbitrary? You know, the same space-time. Firstly, why is the lapse arbitrary? This m. It's just because you can take t and redefine it as another function of time. So without changing, see, what is the really important physical thing in your choice of t? It's what are your surfaces of constant time. There is a much less important thing, which is what values of time do you assign to the surface. The really physically important thing is how you're slicing space-time. You're taking your space and you're slicing it up in a certain way. Now that does not change if t goes to a function of time. Just a function only of time. Then that does not change. But if you change that, clearly you change this lapse vector. Right? Because the dt squared will pick up a function of t dependence.
But in any problem you can set a cross term to be 0 and...
Oh, actually you could. You could go for Gaussian, you know, so normal coordinates, Gaussian normal coordinates. I mean, you could if you wanted to, and in fact, in many situations you actually do. You can choose, at least in a region, you can always choose the lapse vector to be 1 and the shift vector to be 0. And this is often a very useful choice when you're using this to solve problems in general relativity. But if we'd done this from the beginning, what would we have lost? We'd have lost these equations. Because suppose we'd set them to something constant at the beginning, then we would not have been able to vary with respect to them. So for formal purposes, it's a very bad idea to set gauges before you compute equations of motion. As all of you know, this is a terrible thing to do because you miss equations of motion. Okay? So when there are two different purposes for which you might want to solve this. One is actually a computational tool. You are a numerical general relativist, you want to solve for the future. For that purpose, once you've done all this work, you can set the shift and lapse to something useful. This is just a choice of...
I mean, that has to be done before we, I mean, at the beginning.
At
right?
the beginning. You say, I work with a coordinate system in which the shift is 0 and the lapse is 1. Nobody can, at least in an open set.
So wouldn't one miss some important information even then?
No, one misses no information once we've derived the equations. Because we've done all the work.
Yeah.
After that, you can work in any gauge you want.
Yeah. Totally.
We have 4 coordinate variances. We can use that to set the lapse and shift to be anything we want. So let's imagine we've done that. Okay. After we do all this, we set the lapse to something, shift to something else, 0, 1, blah, blah. Okay. We've done that. Then what is the structure of the problem of general relativity? Let's you specify data on a slice and evolve forward. This is how you evolve this and the other guy which I've not even written, which is h dot is equal to the stuff we've written many times. Okay? This gives you the initial value problem, but not for arbitrary initial conditions. Only initial conditions that obey these constraints. So we say the structure of general relativity is an initial value problem. It's an initial value problem in the usual data. The data is h and h dot on one slice, and you time evolve it into the future, however in the presence of constraints. Now I wanted to ask somebody, do you know what this is a very complicated structure, and we've more or less just gone through it. What have we not done in this class? There are two things that we have, two derivations we've not gone through. A, the derivation of Gauss-Kodacki, which is an omission and which I'll make up in an exercise. Okay, it's a classic derivation which you should see. Secondly, the derivation of this equation from here, which is not really an omission. You know, after going through it, you don't feel you've learned anything. And it's a hard calculation. I won't even put it in as an exercise. Okay, it'll take you a long time to get it straight. I don't think you learn very much. Okay, you trust the guy who's done it. York worked it out in a paper in 1979. Okay, okay, he's done it right. Okay. Okay, great. So, but apart from that, we've gone through the structure of everything. You understand we've gone through the in less cartoon detail than we did last time. I wanted to do this so that A, you understand the general relativity is an initial value problem, and B, that you understand that it's an non-standard initial value problem because it has constraints. Now, but now the next question we're going to ask is how non-standard is it? Have you ever seen this kind of system before? And you have in Maxwell electrodynamics. So can somebody tell me, suppose I try to set up Maxwell electrodynamics as an initial value problem, and I time slice it along slice of constant time, because time is not dynamical here. So I choose some Lorentz frame. Okay, something ugly about that because I breaking Lorentz invariance. But okay, I choose one Lorentz frame, I choose slice of constant time. Now can you tell me, Maxwell's equations are 4 in number. How should I think of them in this language? The divergence equation. So the rest of the 3 are the dynamical equations. Exactly right.
Divergence
He means
equals 0 and the source free equations are the constraints, right?
He means the 0 component. Let's look at that. I just want to show this to you because it's so much simpler and you can see it very clearly. Many things are very clear. They're all true for Einstein's equations itself. It's just a souped up version of something you already always known in electromagnetism. Okay. So first thing, you take Fmn, Fmn. And you write this as 2 times F0m, F0m plus 0I, F0I plus Fij, Fij. And then you write everything in terms of lowers. Okay. So you write this as 2 minus 2 F0I, F0I plus Fij, Fij. This is your Lagrangian up to some overall constant. First thing we had here was that there were variables whose time derivatives never appeared in the action. How many of them were there here? 4 of them. There were 3 NAs and 1 M. Are there any variables here whose time derivatives never appear in the action? There's one, which is A0. So A0 is the analog of our lapse and shift vectors. In this case, there's only one. Okay, so if you work out a Hamiltonian formalism for this problem, you will find that there is one variable whose momentum is always 0. That will be A0. The remaining 3 variables all have time derivatives. What is the momentum conjugate to AI? EI, F0I, right? Because F0I involves del 0 AI. So when I take derivative with respect to del 0 AI, let me put by 4, minus 1 by 4. So when I put minus 1 by 4, this is half and this is minus half. Kinetic minus potential. 1 by 4. Thank you. Kinetic minus potential. This is kinetic because it has del 0 AI. So here what we get is that pi I is equal to F0I, including the factors of 2 and the signs here. Okay. Now let me work out the Hamiltonian. Okay. So let's work this out in a little more detail. Pi I was equal to del 0 AI minus del I A0. What? Or AI dot is equal to pi I plus del I A0, which is equal to F0I plus del I A0. So what is the Einsteinian analog of F0I? KB. It was the momentum. Okay? What is the Einsteinian analog of this equation? HAB dot is some KB plus del A and B. KB like the momentum plus del IA times the one field that has no time derivative, the constraint field, the Lagrange multiplier. Let's call any field with no time derivative, let's call it a Lagrange multiplier. So once again we have AI dot is equal to pi I plus del IA0. Del I times Lagrange multiplier, very similar structure. Okay. Now let's work out the Hamiltonian. Okay, let's work out the Hamiltonian. The Hamiltonian is what? Well, this part goes around for the right, it switches sign. So H is equal to Fij by 4. What's the analog of this term? Einsteinian analog? R3. Okay? What happens to this? Well, you see, this almost becomes switch sign, except that this quantity here, AI dot is not quite F0i. It's F0i minus del IA0. Okay, so one term will be just switching sign of this. What was the analog of this term? I'm sorry, I'm overdoing it, but KB minus K square H, K square. Okay, again, just switch sign. But we also got some additional piece. That additional piece, yeah, is minus del IA0 times what? Times F0i. Okay? So this is the Hamiltonian of the gauge theory. This is all in terms of, you know, the variables and the momentum. But there's this irritating other thing. We deal with this, we're not so careful about boundary terms usually, and by integrating by parts. And then, we say, well, there's an equation of motion here. When we vary with respect to A0, and what is the analog, what is that equation of motion called? Constraint equation, Gauss law, electromagnetism. Del dot E is equal to 0. If there was a charge current, the A0 would also couple to the charge current. And so del dot E would be equal to charge. Okay, so the equation for A0 is the constraint. Okay? And that is the Gauss law. And then you have in addition this stuff. Okay? So what we have here is completely analogous structure, and every time you're confused about something in general relativity, you go back to this simple system, which we can work out in 5 minutes. We have worked out in 5 minutes, and check what you get. Okay? Actually, the many, especially when you move to the quantum theory, or there are many more interesting parallels. One of which is that the integral over A0 generates gauge transformations. And it's this integral over A0 that ensures that when you slice the quantum path integral, your Hilbert space only contains gauge invariant states that are invariant under gauge. This is a completely analogous statement in general relativity, because the constraints generate spatial diffeomorphism and time diffeomorphism. Okay? This is a very, very, very similar statement, but we'll stop that. We'll stop our discussion of it at this point. There's one last thing I wanted to say about Maxwell electrodynamics that sort of makes it sort of, well, can you guys stay like 10 minutes more? 6, 5, 6, 10. Okay, I wanted to finish computing one or two things as well. And then we end this module of the course. Okay, there's one last thing I wanted to say about Maxwell electrodynamics, which is this. That you see, what equation was the constraint equation was the A0 equation. Now we said this in this Hamiltonian language, but we didn't need to. We could work out the A0 equation just in Lagrangian language. What equation was that? That was del mu f mu 0 is equal to 0. That's the equation you get from varying with respect to a0. From this language, can you tell me why the constraint equation never has a double time derivative? Exactly. So you see, the fact that the constraint equation in Hamiltonian language, the fact, see, what was the constraint equation was constraining data, was constraining momenta and coordinates. In Lagrangian language, that's an equation that it doesn't involve a second derivative of time. Okay? Here, f0i, well, f0, 0 is 0. So this is the same as del I f0i. And f0i has a time derivative, but you only add spatial derivatives to that. So clearly this thing is one derivative in time. Lastly, I want to see that this other property of Einstein's that we talked about at the last class is obeyed at Maxwell's equations. I want to see that if the constraint equation is obeyed at one time and the dynamical equation is obeyed at all time, then the constraint equation will also be obeyed at all time. Let me prove that. Again, in the case of Maxwell's equations, it's a 2-line proof or 3-line proof. Let's see. Okay. What I want to do is to check whether del 0 of del I want to see what that is.
By antisymmetry.
Exactly.
And the symmetry of these two derivatives.
Exactly. So now, so the first thing I do is say that by I'll change these two. So I'll make this del I. Now I'll use Maxwell's equations, the ith component of Maxwell's equations, the dynamical equation, which I'm going to allow myself to use. Exactly. Do you understand? So this will be minus del I del j f j I. What? Plus, maybe plus. Oh, plus source term. Plus source term. It's true. Plus source term. But you see, the constraint equation itself involves sources. Let's set sources to 0 for a moment. We'd have to do the whole thing again, because then we would have to have the J0 part on the right hand side as well. Okay? The source term will also work out because it's conserved. Okay, but let's ignore that for a moment. For instance, we didn't put in matter into our analysis of Einstein's equation. Let's take the direct analog of that. Okay? But this is equal to 0 because this is symmetric and this is antisymmetric. What have we used from going from here to here? The I component of Maxwell's equations. Only spatial components. These are the dynamic equations. So I have shown you that not assuming the constraint equation, I've shown you that the time derivative of the constraint equation vanishes as a consequence of the dynamic equation. So the constraint equation looked like 4-dimensional data, some equation that was true at all space-time. But actually it already followed from the dynamical equations that the time derivative of the constraint equation was 0. So the only additional piece of information in the constraint equation is that the value of this derivative, which is a function of x, is everywhere 0. So it's one function of space, but not of time. Or another way of saying it is that if you arrange for the constraint equation to be satisfied in one slice, it will automatically be satisfied on every other slice, assuming only that the dynamical equations have been obeyed. Constraint equations tell you what data is allowed is consistently time evolvable. And it would have been very bad news if you started with time evolvable data and evolved to non-time evolvable data. It would have meant that you were in an inconsistent theory. The fact that data that obeys the constraints evolves to data that obeys the constraints, of course, comes from the fact that these are well-posed systems. But of course, can just be proved here. Okay, exercise. Prove the same statement for Einstein general relativity. if you get very badly stuck, let me tell you, walled. It's a very simple proof. It doesn't require algebra. You just have to think. And there's a nice discussion in Wald about it. Okay, so if you get proofs in. Okay, well, unless there are urgent questions, I'll move on to the last thing I wanted to say. Questions, comments?
So you're saying that if we set the initial condition at some time and evolving it to some time, and if we consider that to be another initial condition, that it should satisfy the constant equation again.
If you satisfy the initial conditions, once you give me initial conditions, the dynamical equations are sufficient to evolve the data. I don't need to tell you about the constraint equations. For any data,
the initial conditions must be consistent with the constraints.
Yeah, but as a mathematical problem, for any data, you can evolve that data to the future, whether or not it obeys the constraints.
Yeah.
Now, if you start out with data that obeys the constraints,
then it will always satisfy the
it will always evolve to data that also satisfies it.
Because we can take that also
As
as an initial condition again.
For the next step of evolution. So it had better be true, but it comes out.
So this would imply that quantum gravity is also a unitary theory.
Yeah, well, this would, see, this is at the moment just a statement that the equations of motion classically are consistent. If this had not happened, it would have said that it was just an ill-posed system of equations. Okay, you could never find or at least you find many fewer solutions, because the solution has to satisfy the constraints everywhere, and also has to satisfy the dynamical equations everywhere. If there's a clash between the two, you're in trouble.
So what does this imply for quantum gravity?
At the moment implies nothing. For it's telling you that classically it's a well-posed system. And to the level of canonical quantization, it appears to give you a well-posed quantum gravity problem, maybe. Okay, but as you know, there are many steps between that and getting a genuine quantum gravity problem. This does not seem like the right way to quantize gravity. No attempt using it has succeeded. Many people tried. Many people tried. I mean, Dirac tried in the 1930s. It's a natural thing to do.
But I mean, when Dirac said that, the Hamiltonian formalism of general relativity was not there, I guess.
No. But Dirac was very good at making Hamiltonians. he was trying. And this formalism wasn't there, but some rough. It's remarkable what a prescient man Dirac was. Within a year of completing, within a year of 1928 to 1929 or whatever it was, where he felt he totally understood quantum mechanics, he was seriously in his mind pursuing quantum field theory, including questions about gravity. It's this remarkable statement in a letter, somebody saying, at some point we'll get to the question of why the structure of the universe is the way it is, and maybe it has its origins in quantum fluctuations of the initial state. I mean, totally, this is what the theory of inflation asserts. It's totally remarkable that somebody in the 30s can write something like that. Whether or not it was, I mean, he didn't know it was true, but that he could. Yeah, he was very remarkable. He could at least vaguely. So he was trying many things. Yeah. So as you say, Ashtekar, the whole formalism of canonical quantum gravity has been attempted many times, but in my opinion, basically no success. For instance, that program does not seem to produce flat space as a solution. And therefore doesn't seem to produce classical gravity as a limit. And so it produces something, but it's not clear one should call it quantum gravity, in my opinion, because it is not a theory which has a classical limit that becomes the theory we started with. And it's not because these guys are stupid, they're not. It's not because this was an unnatural thing to do, it's not. But it doesn't work. It doesn't work probably because quantizing gravity is not.
I mean, one starts with the classical Hamiltonian and then quantizes it, but magically the classical result is not, the classical limit is not 10.
You have to find a state in that Hilbert space that roughly looks like flat space. far as I have seen, nobody has ever shown me a stated their Hilbert space that looks like that. Every time somebody's attempted to show that, somebody else finds why what this, usually Witten finds why it's wrong.
There are also problems with Lorentz anyway.
There are many issues, but in my opinion, at least I have not studied the subject very carefully, but to the extent that I have had conversations with people, I have not seen a systematic place in that program which reduces to classical gravity and therefore can compute corrections for classical results. If somebody can give me a formula, however they get it, scattering of 4 gravitons, that corrects Einstein's gravity. You give me the formula, I'll test it the way I want to test it. I'll check unitarity, I'll check it. Okay. Far from that. Because there's no space in which to scatter. This, by the way, just to say we should get a more serious stuff in 1 minute. I'll do that. But since it's an important problem, again I want to emphasize that it's not because anyone is stupid or something like that. That's certainly not the case. It's a very hard problem. And why is it a hard problem? The underlying reason that any such thing is going to be very hard is the problem we encountered in like our 3rd lecture of general relativity, which is the scale hierarchy between the cosmological constant and Einstein gravity. Anything non-sophisticated you do, quantum mechanically, will disturb that hierarchy. Now the hierarchy is infinite if you have flat space, because then the cosmological constant is 0. And it's parametrically large if you have a parametrically big space. If you have a space much bigger in curvatures than Newton's constant, than the Planck scale. And not just them, no string theorist as far as I can tell, string theory has not yet understood how to produce such a hierarchy in the absence of a symmetry that protects it. And there's one symmetry that we know of that protects it beautifully, which is supersymmetry. Okay? And so every serious success of producing real quantum theories of gravity in string theory employs supersymmetry, because it is the symmetry that stabilizes this hierarchy and thereby allows you to calculate. Any attempt, even within string theory, that lacks the supersymmetry has not worked, because we have not yet understood another mechanism of stabilizing this hierarchy. So there's some, supersymmetry is a fantastic thing, but does not seem to be experimentally realized at low energies in our universe. Does not seem to be the mechanism employed to stabilize the cosmological constant in our universe. It's not just the loop quantum people, also the string people, also all of us are missing something very important. And that is everything else one can get around, perhaps, if you're clever enough. But this is a fundamental thing. If anyone tells you there's a used car salesman who comes to sell you a quantum theory of gravity without supersymmetry, claims it's in flat space, the first thing you have to ask yourself is, why is it not true that quantum loops are generating a huge cosmological constant? Unless you can clearly answer that question, don't buy that used car. This is my advice. And I do want to emphasize that this is not a community versus community kind of fight. We have the same problem. Without supersymmetry, we've not solved that. And this should be said very loudly, because it's a failure of every human attempt to find non-supersymmetric quantum gravity so far. And it's a great opportunity for you young guys, because you'll be famous if you solve it. Okay, fine. Last 2-3 minutes. I should have. Okay. The last 2-3 minutes, I wanted to go back to there's all this in principle business that we wanted to do. Why have we gone through this canonical formulation of general relativity? Is it because we use it very often? Not very often. When we want to find the Schwarzschild solution, we didn't write it in terms of P and it was not needed, right? We just wrote down the beautiful, started here, we used our nose, we managed things. Maybe some numerical people use it, but why was it of so much interest to us? A, because just to understand the structures a bit. That's always nice. B, second, because Upmanyu wanted it. But third, because it leads us to the notion of energy. Okay? That is a very important thing. Okay? So the last take-home message we want to take from this is about the notion of energy. So let's very quickly go through that part. Okay? So what we had was that the Hamiltonian on shell evaluated only to purely boundary term. Now this boundary term involved two parts. One part was integral of little k, and the second part was the integral that came from the other boundary.
From the Hamiltonian itself.
Exactly, from the Hamiltonian itself, which was basically n, let me write it down. KAB minus KHAB times NA this is normal to the surface. Exactly, 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 exactly. Now, if we want to work with something we think of as time evolution, okay, 2-3 minutes, okay, what we're going to do is this. If we want to, so far what we've been doing is something abstract, right? We've got some arbitrary slicing of our space-time. We called it time, but that was in our head. Now we want to deal with real time. Okay? What does that mean? We want to restrict attention to space-times that at very large distances become approximately flat space. And then what we will do, if we want to evolve in time, we want our t vector to run along d by dt of the genuine flat space-time. Otherwise, we're not going to compute energy. Our Hamiltonian will not generate.
Could you please repeat that?
Yes. So we have this abstract, okay, so we've got, let me draw a picture. Okay, I've got the space-time, some very complicated mess in the middle. But outside, it's reduced to flat space. Okay, we go far away, it's like a black hole. I mean, it's far away.
What if it's ADS or TS then asymptotically even?
Every such example will have to be reanalyzed. But let's say that our equations of motion are Einstein's equations without a cosmological constant. Then it cannot be ADS. So let's look at it. Look, every such question you have to reanalyze. The notion of energy, because the notion of energy in general relativity is a notion evaluated at infinity. The structure of infinity is very important to discussing the notion of energy. Okay? It's not something that you can locally apply to all space-times. Okay? So in order to, and that becomes clear because energy by its nature is a conserved quantity conjugate to a time. Unless you know something about what time you want it to be conjugate to, which is a function of what space you're living in. You cannot even begin the discussion. Okay? Let's focus on asymptotically flat spaces. Some complicated thing and outside far away is asymptotically flat. It's just basically flat space. Now, what we did was to choose an arbitrary slicing. What we will demand now that this slicing can be arbitrary in the middle, but at infinity goes over to actual slices of constant time. Moreover, we will demand that a time coordinate at infinity goes over to actual time. So that fixes the lapse function. Moreover, we will demand that our NAs go to 0. Because we don't want the thing that will generate time translations and some space translations. We want the thing that will generate time translations. So we will demand that this thing go to 0. These NAs go to 0. Exactly like we did in our derivation. May be possible to do our derivations with more general assumptions, but for this problem we don't need it. Okay? So in this case, this guy is just 0. because the NAs are 0. Okay? So the energy is purely the integral of the space, the energy is purely given by the integral over the extrinsic curvature of a constant time slice evaluated on the two-sphere at infinity. Okay?
So I'm a little confused about that one. Why does the bulk term not constitute?
Bulk term, because the constraint equations are.
Because of the constraint. On to the right.
Is this clear? And therefore, if you want to evaluate the energy of a space-time, what you should do is to evaluate the extrinsic curvature of a constant time slice at infinity. Now there is one complication, and this complication is resolved in different ways in different asymptotic backwards. And that is that if you take, if you evaluate the extrinsic curvature, so let's take just plain flat space. A spatial slice t equals constant. Spatial surface is two-sphere because time slice. Okay. Now, if you evaluate the extrinsic curvature of the two-sphere, extrinsic curvature is a one-derivative object, so it would be roughly speaking 1 over r. Some number times 1 over r. Then you take that and you integrate it over the two-dimensional two-sphere.
Blows up.
This is r squared, so it blows up. So you see, the problem is that this is a nice quantity, but it doesn't even evaluate to 0 in what you might think of as the space which you would like to assign 0 energy. Therefore, it will not it will evaluate as something very divergent, also for a Schwarzschild black hole, because Schwarzschild black hole roughly goes to flat space. So the prescription that is adopted is this. What you do is this, that is, you compute the value of this quantity minus the value in flat space. Now you have to make that precise. So what you do is this. What you do is to take, you cut off and you look at your surface at infinity. Okay, you do some cutoff. When your surface is very large, because space-time is asymptotically flat, this surface can be embedded into actual flat space, by which I mean there is some embedding of actual flat space will give you a surface with the same intrinsic metric. Will have different extrinsic geometry. Okay, this is possible. So what you do is now consider evaluating square root h times k on your space. Subtract square root h times k of the space with the identical geometry, identical intrinsic geometry embedded in flat space. And I emphasize identical. You cannot
identical of the hypersurface, of the spatial hypersurface.
The intrinsic geometry of your hypersurface has to be exactly the same. You are not allowed to make mistakes of order 1 by r, because remember, the quantity you're getting from both things diverges. If you make a mistake of order 1 by r, you can get something wrong in the finite part. Okay? So you have to get the identical geometry. Then do the subtraction. And that gives you the energy of your space-time. Okay? The rationale for that is that, if you're one way. Okay, let's talk about that in a minute. First, let's understand the prescription. Okay, is the prescription clear? Okay, so take your geometry. Evaluate square root h times k. Put some cutoff at infinity, very large. Evaluate square root h times k. Then evaluate square root h times k for another problem. The other problem is flat space with some surface chosen so that this space-time, so that on that surface you have exactly the same intrinsic geometry as in the physical problem, as in the cutoff physical problem.
In other words, H should be the same.
H should be the same, exactly. Okay. Now, I want to very quickly show you how that works for a Schwarzschild metric. Okay. I'll leave you to fill out the numbers. It's 6:30 almost. I'll leave you to fill out the numbers yourself, but I want to show you the main idea. Okay, and I'll leave you to fill out the numbers as an exercise. Okay. So what's the Schwarzschild metric? dr squared is equal to minus 1 minus 2m by r dt squared plus dr squared over 1 minus 2m by r plus r squared d omega d minus 2 square. Now what is our prescription? Our prescription is, let us work at we will choose R once again to be capital R, so that the intrinsic geometries of the problems are exactly the same. Now what I'm supposed to do, again I just throw this away. What I'm supposed to do in both these problems is to compute the extrinsic curvature, the trace of the extrinsic curvature of the surface R is equal to R.
Now that will depend in general on the M.
That will depend on M. Let's see how it depends on M.
Because there will be some component which is perpendicular to the height of surface.
Well, let's see. In this case, let's just compute the normal. The normal one form is dr. But what is the normalized normal one?
Square root of 1 minus
dr by square root of 1 minus 2m by r, because G upper has it upstairs. Okay? So what we're going to get, okay, and then after we've done the computation, we will do some dotting. We'll trace the curvature, but that trace is purely in this intrinsic metric. Okay? So where is the difference going to be between these two problems? Only in this factor. So I will get some answer which will differ how? It will just differ by the fact the answer for this problem having this factor x. Now we've seen what we expect. We will get something, some number by r. Then we'll get 4 pi r squared. So we will get 4 pi times some number without a pi. 4 pi times some number without a pi, some number times r, into 1 over square root of 1 minus 2m by r minus 1. Okay, so this will be 4 pi times some number times r times m by r. No, not r squared, because you see the extrinsic curvature of a large sphere is 1 by r.
Yeah.
Okay. This r and r cancels exactly. Higher order subleading if we ignore them. So it's some 4 pi times some number. Now you might times m. Now you might worry, what about pi? What's the deal with pi? This some number, whatever it is, will not involve a pi.
Yeah, but there's a 16 pi.
Exactly. There was a factor of 2 as well, so it was actually 1 by 8 pi. So there's a 1 by 8 pi times all of this. So that's the deal with the 4 pi's. And then you have to get that sum number right, and that sum number will be it. Okay? So basically it's that simple. Okay? But exercise, do this carefully. Compute the ADM mass for a Schwarzschild battery. And check that it's M.
So we have to be careful about the subtraction, and in that 2 space, I mean, the certainty that you had discussed. I mean, it will
But
not
here,
simply be the Gibbons-Hawking term, but the modified.
it's the Gibbons-Hawking term on a constant time slice, and this other term that was a subtlety plays no role because n has gone to 0.
No, no, I mean, in the original boundary term, I mean, it's locally.
It's on a constant time slice. It's this k, right? Yeah.
Okay, yeah. It's
this not the whole thing. Okay. Excellent. I have one last thing to say, and that's this. We computed this ADM mass at a constant time slice. Now you can ask, is this conserved? Now, after all, energy is a useful notion when it's conserved. Often. Okay? And these questions are slightly odd one, because it depends on what you're doing.
So, I mean, if Hamiltonian, I mean, use the intuition from classical mechanics, if Hamiltonian has no explicit time dependence, then it will be conserved.
Right. But, you know, does our Hamiltonian have an explicit time dependence? All these k's, for instance. It's a confusing question, I think, about which background. Let's ask what it means firstly for it to be conserved. You see, our Hamiltonian, the value of Hamiltonian is a boundary term. Let's say I evaluated at some fixed r and then evolved in time. Would that be conserved? This is slightly confusing if we're really thinking of asymptotically flat space, because if I've got some radiation that goes out at some point, surely the space within that fixed r loses energy, because energy has gone out. But okay.
The metric wouldn't be asymptotically Minkowskian.
No.
If in a radiative solution.
Well, it's decay. Radiation can be very small and yet carry finite energy. Okay. But of course, you know, that's a trivial thing, because you've just not gone far out enough. You should be so far out that you contain all your radiation. So what you should do is, as this thought experiment makes clear, if you want to calculate all the energy in your space, including all the radiation, is first take r to infinity. And then any process that happens in some finite space will not have time to reach infinity, and just causality will ensure that the energy is conserved. Because all we're doing is computing something at very, very far away on a surface, and then nothing happens in that surface. So of course it's
So this is a matter of taking the appropriate order of limits?
yeah, it's almost like, it almost feels conserved by definition. Because, you know, you're evaluating something very far away on a boundary, and then by causality nothing affects that boundary. So of course it doesn't change with time. However, there's something else one can do, okay, which is a little more interesting, which is this. One can now, you see, we have this two-sphere at infinity, and this two-sphere was both at fixed time and fixed r. Now what one can do is to go to a coordinate which is r plus t and r minus t. So if you're at fixed time and fixed r, you're also at fixed r plus t and you're at fixed r minus t. But now that allows you to take some things to infinity, and work on this part of the Penrose diagram. We previously were talking about this part of the Penrose diagram, r going to the infinity at all. Now you can work at this part of the Penrose diagram. In this, here, will this energy be conserved as you move along here? No, because of energy, radiation goes out here, you don't count it anymore here. So in fact, if you move this way, energy as a function of where you are in Scri plus will always decrease. The difference between this energy you calculate here minus the energy you calculate here must be the energy that's radiated out in the meanwhile. Okay? And this is true and can be made precise. You can associate a certain energy with the radiation, and talk about a conserved quantity if you include also in that conservation law the radiation energy. Like that, exactly. Okay, this we will in the first lecture, next class, discuss a little more in detail, because it's practically important. We need to know how to associate energy with radiation. LIGO people want to know this, so we should study it. Okay, great. Thank you.